Okay, so in section 6.5, these applications of area between curves, one of the applications is consumer surplus and producer surplus. So for consumers, the demand curve, P equals D of X, represents the price consumers are willing to pay. And then S of X, the supply curve, represents the price at which producers are willing to sell their product. There's this equilibrium point where everybody's happy. And that's this point X sub E, P sub E for equilibrium. That's where the two curves meet. That's the intersection point of the two curves. So you've got the demand curve like this and the supply curve like this, and this point is their equilibrium. So X sub E, P sub E. There are some consumers who are willing to pay a price that's higher than the equilibrium price. So if they pay lesser than that, then they've saved money. That's called this consumer surplus. So that is actually this value right here. So it's going to be that area, that's the consumer surplus. So if you guys, you know this with your business minds, but the supply curve is like here, maybe, and see if I can draw that 3 times. Well, this is your supply curve. So this first picture shows us the total value to the consumer. That's that entire area. So this whole area is the total value to the consumer. This is the actual total cost to the consumer, that box. And then this portion right here between the equilibrium point and the demand curve. So that's where the consumers are going to pay a higher price than the equilibrium price. So if they pay less, then they're saving money. This is called the consumer surplus. Okay, so that area, this is the area between two curves. So that area is going to be the top function, the integral of the top minus the bottom, which would be equal to the demand curve minus P sub E. If you looked at this as like Y equals P sub E, that would be your bottom function. So this is this dx from 0 to the equilibrium X value. So from 0 all the way to X sub E. And then if you actually work through this and do the integral, since this is a constant, you're just gonna, like you can, when you do that integral, the same thing will happen every time, and it'll just pop out with the X sub E. So this would be the integral of the demand curve dx minus P sub E times X sub E. Because the other one would be 0 and it would just go away. So this is no longer in the integral, but the demand curve is. So in the same way, there are producers who are willing to sell at a lower price than the equilibrium price. So if they sell at a higher price, then they've made money. That's called producer surplus. So let's look at that sort of similarly. So we have the supply curve, and then in each of these, the demand curve, the demand curve is coming in like this, say. Let's pretend that went through there. Let's pretend all these look the same. So this is your demand curve over and over again. So this is the total value to producers, this area down here. This is actually the total cost to produce, to the total cost to consumers still, the same as it was before. Total cost to consumers. And then this last box here, so remember the consumer surplus is up here. this is the producer surplus, this area here between that equilibrium spot there and the supply curve. This is S there. So that region is producer surplus. All right. So when we do this, producer surplus is defined to be the same thing that we're going to do top minus bottom here. So we're talking about this area. So the top function is P sub E. We're evaluating from 0 to X sub E. Minus the bottom function, which in this case is the supply, dx. And then when you do this, similarly, that P sub E, X sub E will sort of fall out, and then you can just take the integral from 0 to X sub E of S of X dx. Sorry, I'm talking really fast. I have been teaching for hours and hours today, and I think I'm perhaps at my limit, but I need to get this posted for y'all today. Hopefully it'll still be helpful, or you can slow me down when you watch this back later. So that is producer surplus. So let's do a couple of examples with that, and then we'll talk about the Lorenz curves as well. So the demand function for a particular product is given by this function d of x equals 24 minus 0.6x minus 0.03x squared. So this looks like this somehow. If X sub E is 10 units, so this is X sub E, where it would run into this is 10. Find the consumer surplus. So consumer surplus is this area here. So we're going to do the integral from 0 to 10 of d of x dx minus, and you can set this up. So top minus bottom. So top would be 24 minus 0.6x minus 0.03x squared. Minus the bottom function there would be P sub E. So the question is, okay, well, what is P sub E? Hopefully that is your question. So what we're going to do, is figure out what the demand is at 10, because that would give us, or X sub E, right? That would give us P sub E. So if you plug in 10 there, you have 24 minus 0.6 times 10 minus 0.03 times 10 squared. So 24 plus 6 plus 3, 24 minus 6 minus 3. So 24 minus 9 is 15. So then we're going to use that in our stuff. So the integral from 0 to 10 of 24 minus 0.6x minus 0.03x squared minus P sub E, which is 15 dx. Keep going there. 24 minus 15 is 9. Minus 0.6x minus 0.03x squared, just combining like terms before I take an integral. And then doing the integral, I have 9x minus 0.6x squared over 2 minus 0.03x cubed over 3. This is evaluated from 0 to 10. And when you do that, you get 50. So that is the consumer surplus. Okay, producer surplus. Here's our example of this. We're going to look at the supply curve, which is coming up like this. And then here is our equilibrium thing. So this is X sub E, P sub E. X sub E here happens at 5. That's what's given in the question. Producer surplus is this area right here. So we're going to do the integral from 0 to 5 of the top function, which is going to be P sub E, minus the bottom function, which is going to be S of X, which is 9e to the 0.4x dx. Okay, and then when you do this, you get, that's a U substitution there. The 9e to the 0.4x, but P sub E times X minus 9e to the 0.4x divided by 0.4. And this is evaluated from 0 to 5. Okay, I need to figure out what P sub E is. So I'm going to do S of X sub E, which is 5. So I have 9 times e to the 0.4 times 5, which is 66.502. So I have 66.502x minus 9 divided by 0.4 e to the 0.4x. And this is evaluated from 0 to 5. That's a lot of stuff happening there. When you do this, I have 166.256 minus negative 22.5. So 188.756. And that is the producer surplus. So again, I just set these up like area problems. So sketch the demand curve, sketch that equilibrium line, and then do top minus the bottom. Or for producer surplus, sketch the supply line, the supply curve, and then the equilibrium line, and do top minus bottom. Okay, so another application for area between curves is the Lorenz curves. So they are actually, this is kind of fascinating, honestly. The Lorenz curves are used to sort of measure the distribution of income in a society. So each value of X between 0 and 1, the value represents the percentage of the country's total income earned by the bottom X percent of families. So this first example will help us understand what the heck that means. So if Y is 0.5x squared plus 0.5x, this is the Lorenz curve for some country or a society. We're going to find F of 0.25. So F of 0.25 would be 0.5 times 0.25 squared plus 0.5 times 0.25. And when you do this, you get 0.15625. So the bottom 25% of the way we interpret this, because this is the total income earned by the bottom X percent. So the bottom 25% of the population accounts for about 16% of the total income. So if it was like perfectly distributed, then the 25% of the population would account for 25 of the total income. But this 25% of the population is accounting for only 16%. That's a little bit out of equilibrium, I guess. And we'll talk about that in a minute, how we measure how far out of equilibrium something is. All right, so if every family had the same income, what function would represent the Lorenz curve? That means everything is absolute equality. Everything is distributed perfectly. That would be f of x equals x. This is absolute equality. That would mean that f of 0.5, which is 0.5, is that 50% of the population, the bottom 50%, accounts for 50% of the income. That's, perfect, right? So that's absolute equality. If instead one family had all of the income, what function will represent the Lorenz curve? Well, it would be 0, 0, 0, 0, 0, and then boop, and that one family would make all of the money. So f of x would be equal to 0 for x less than 1, and would be not less than or equal to, just less than 1, and then would be 1 at that spot when x equals 1. So that one family accounts for 100% of the population. So there's actually no area there because this is absolute inequality. Okay, so these are two extremes. And the idea is that everything falls between them. Those two extremes are, let me highlight this, is this down here. This is absolute inequality. This is absolute equality. So the idea is that a Lorenz curve is going to fall between them. And so we want to like measure how far off a curve is from equality by doing the area ratio, a ratio of this area, call this area 1 and this area 2. So the ratio between y equals x and f of x with the area under y equals x. Oh, no. So the big area here, the triangle, this would be the triangle, and then this would be the little region. So region over triangle. So you take the ratio of the area between y equals x and y equals f of x. That's your region here. And you're going to divide it by the area between y equals x, absolute inequality, and y equals 0. I mean, absolute equality, absolute inequality. So this would be equal to the integral from 0 to 1 of x minus f of x, so top minus bottom dx, over the integral from 0 to 1 of x minus 0 dx. So this is the bottom here would be x squared over 2 when you take that integral. So that would be an evaluated from 0 to 1. So you would have 1/2 minus 0. So this is 1/2 on the bottom. And then on the top, you just have that same thing. So the integral from 0 to 1 of x minus f of x dx. So I don't like this whole dividing by a 1/2. So I'm instead going to multiply by 2 because that would be the same. So let's see, go from 2 times the integral from 0 to 1 of x minus f of x dx. So again, that 2 is coming from this 1/2, just like multiply the top and bottom by 1/2. 2 over 1, sorry. Yeah. A 2 over 1, because those will cancel on the bottom, and then push that 2 to the top. So that's where this 2 comes from. So the coefficient of inequality is how far from equality, from absolute equality, the Lorenz curve is. I don't know why I'm trying to write this right here. Okay, so if we are looking at, actually, we've done this. This is it. Maybe some parentheses here to make that easier to read. So there was a lot of stuff that just happened, but what is going on is you're looking at this area, the ratio of that divided by the rate divided by this, and that tells you like how far off from equality you are. And so when you actually work that out, because of this triangle and this being 0, that bottom integral is 1/2, and it's on the bottom of a fraction. So it's the same thing as multiplying by 2. So that is how you find the coefficient of inequality, and that is why an area between curves application here. So the income distribution of a small country is estimated by the Lorenz curve given by this function f of x. What percentage of the country's total income is earned by the lower 80% of its families? So we are going to do f of 80. That will tell us, f of 0.8. It will tell us what 80%, the lower 80% of the population contributes to the economy. So we have f of 0.8 is 13 over 18 times 0.8 squared plus 5 over 18 times 0.8. This is going to be equal to 0.6844. So about 68% of the population of the income is earned by the lower 80%. So that's not equality, right? Because if it was at equilibrium or at absolute equality, 80% of the families would account for 80% of the income, and this is only at 68. So how far off are we? We're going to use the coefficient of inequality. We have a coefficient of inequality. I don't know, let's call it a COI. This is 2 times the integral from 0 to 1 of x minus f of x dx. So when we plug in our stuff here, we need to be careful that first thing, this is a minus the whole function, so it's going to distribute to everything. So 13 over 18 x squared plus 5 over 18x dx. So we have 2 times the integral from 0 to 1 of x minus 13 over 18x squared plus 5 over 18x dx. And I could combine like terms there if I wished, which perhaps I do. 18 and, oh, that's a minus. I see, I warned us about this. That's a minus. That minus is going to distribute to there too. So this is like 18 over 18 minus 5 over 18. So that would be 13 over 18. So 2 times the integral from 0 to 1 of negative 13x squared over 18 plus 13x over 18. I just combine like terms there. Obviously, you don't have to do that. And then increase and divide. So negative 13x cubed over 18 times 3. That's the dividing part, divided by 3. Plus 13x squared over 2 times 18. There's a 2 in front of all of this, and this is evaluated from 0 to 1. So 2 times this thing evaluated at 1 minus this thing evaluated at 0. I have 13 over 15 or 0.241. So the coefficient of inequality is 0.241. Oh, I did take a 13 over 18 out of both of these pieces, but to make the arithmetic simpler, I guess. Times negative x cubed over 3 plus x squared over 2, but those evaluated at 1 and 0. Anyway. Okay. Last and not least. So we have the income distribution for a certain country in 1996 was estimated by this function f of x. In 2000, the income distribution was estimated by a different function. Find the coefficient of inequality for each of the years. So let's split this up into 1996 and 2000. So in 1996, we're going to do 2 times the integral from 0 to 1 of x minus f of x dx. So this is the integral from 2 times the integral from 0 to 1 of x minus 0.34x minus 0.66x squared. I went ahead and distributed that minus sign. This is 2 times the integral from 0 to 1 of 0.66x. I would make that a 4 and a 6, minus 0.66x squared. So 2 times 0.66x squared over 2 minus 0.66x cubed over 3. And then you can do that same thing again. This is evaluated from 0 to 1 of 2 times 0.66 x squared over 2 minus x cubed over 3 evaluated from 0 to 1. I have 0.22. And then in 2000, we're going to do 2 times integral from 0 to 1 of x minus f of x dx, finding the coefficient of inequality. So our function here, I'm going to distribute that negative again, 0.3x minus 0.72x squared plus 0.02x cubed dx. X minus, or 1 minus 0.3 would be 0.7x. Minus 0.72x squared plus 0.02x cubed. And then 0.7x squared over 2 minus 0.72x cubed over 3 plus 0.02x to the 4th over 4, evaluated from 0 to 1. And then when you do that, I have 2 times 0.7 over 2 minus 0.72 over 3 plus 0.02 over 4, all of that minus 0. This is 0.23. Okay, so part B on this one says, which had a more equitable income distribution. So this is the measure of how far you are from inequality, from equality. So how far you are from how far you are from equality, how far from absolute equality. So the smaller the smaller the coefficient of inequality is, the more equitable it is. Smaller coefficient of inequality implies that it is more equitable. So 1996, because 0.22 is less than 0.23. So a smaller coefficient of inequality means that it is more equitable, which means that the 1996 Lorenz curve showed a better distribution of finances than the 2001. Okay, so those are 2 examples of 2 applications of really 3: consumer surplus, producer surplus, and the Lorenz curves for 6.5. If you guys have any questions or would like to see any of that in more detail, please let me know. Thank you.